the recording.
Okay.
So hi everyone, my name is Shulei Zhang. So welcome to today's Condensed Matter seminar. It's my pleasure to introduce our today's speaker, Dr. Alessandro Principi. Dr. Principi has been a lecturer in the Department of Physics and Astronomy at the University of Manchester since September 2017. So after he obtained his PhD in 2013 from Scuola Normale Superiore. I think that's part of Pisa University system in Italy. So he worked as, after that, he worked as a postdoc at the University of Missouri, Columbia in the United States, and then at the University of, at the Radboud University, Nijmegen in Netherlands. So during those years, he studied the role of many-body interactions on the transport of dynamical properties of graphenes, van der Waals heterostructures, as well as topological materials, semimetals, etc. He has formed a successful collaboration with world-leading experimental research teams studying hot electron relaxation in graphenes. I think that's including this Andre Geim's team taking advantage of the proximity effect, sort of. Okay, okay. So today, Dr. Principi is going to tell us something about some recent work on thermal transport in clean and I think also compensated semimetals as an application of electron hydrodynamics. So without further ado, Alessandro, please take it away.
Thank you. Thank you very much for the very nice introduction. Let me see. Oh, can you enable my screen sharing?
There you go.
Okay. Do you see my PowerPoint, right?
Yeah, yeah.
Okay, so so please, whenever you want to interrupt me, please interrupt me. I'm very fine getting questions at any point of the talk. So the talk is about electron hydrodynamics in semi-metal, which is a work that has been going on for few years. I would say since I was in basically at the University of Missouri. So I listed here some of collaborations, theory and experiment collaboration, where you can see, of course, Andre Geim and Giovanni Vignale and so on. The most important experimental collaborator actually has been Dennis, who was the first to actually realize the electron hydrodynamics in graphene, and actually then he moved here in Manchester. Then he moved moved at MIT, and now has recently accepted a position at in Singapore. So this work is so what I'm telling you is a story about several works that came out over the years. So there is I will go through several things. But please stop me at any point if you have any question. So the first thing that I want to say is to smoothly introduce the topic. I guess everyone is more or less familiar with hydrodynamics, general hydrodynamics, but I will just repeat everything anyway. So why do we want to study hydrodynamics? Hydrodynamics is a theory that accurately describes transport in liquids, which are in a way strongly interacting system. Strong interacting system because particles interact, bounce against each other frequently enough that they establish a local quasi-equilibrium, and out of this local quasi-equilibrium in the long wavelength regime, one can describe transport in terms of few equations and few coefficients. So these are, of course, the continuity equation, Navier-Stokes equation, which contains two coefficients. One is the kinematic shear viscosity, which is essentially the friction that one experiences when the fluid experiences when it undergoes volume conserving deformation, so of the such. And the other is the kinematic bulk viscosity, which is for our purposes will always be zero, but in general is the friction that the liquid experiences when it goes volume non-conserving transitions. And if you're careful here, you recognize that this is not a real Navier-Stokes equation. There is a friction term here, which normally does not exist in hydrodynamics. This is actually the equation, an equation that can potentially describe an electron fluid, where one has an interaction with an external system, which is can be impurities or phonons and so on. And of course, instead of the pressure, here we have a term which is the electric field. And finally, the last equation is the equation of the continuity equation for heat, the equation of heat transport, which is controlled by the thermal conductivity. And I will talk about, in the rest of the talk, I will talk about these two coefficients, the shear viscosity and the thermal conductivity. So before continuing with the results, let me first ask a question. Why do we can transport in a quantum fluid be hydrodynamics? So at the first slide, in general, it should be possible. It should be quite easy to realize hydrodynamics even in electron fluid. We know that electrons can behave as semi-classical particles in certain regimes. We know that interference effect, which are one of the most quantum effects that we can realize in solids, are unimportant at large enough temperature, or even ballistic transport becomes unimportant at large enough temperatures. So it is possible to have electrons behave as like molecules of a liquid. Interactions are strong. We know that we know from Landau theory that interactions are certainly strong. Interactions are Coulomb interactions, so even stronger than what we can find in liquids. So it is quite puzzling, however, that one has no sign of viscous flow in conventional metals. If you open a standard textbook of solid state, you will see that there is no mention of hydrodynamics. All transport is taken care of by electron impurity scattering or electron phonon scattering. So there is almost no mention of the role of electron-electron interactions in transport. So this, of course, the topic is not too young, as you can see. The first attempts go back to the 1960s. So the idea is that to find conditions for which hydrodynamic can emerge in realistic systems. So first of all, since hydrodynamics is a theory for long wavelength and and slowly varying fields, one has to focus on the limit of small momentum and frequency, and of course one has to go away from the ballistic limit to be able to find hydrodynamics. So it's a regime. Hydrodynamics is a regime in which collisions are important. And in solid, in general, there are a few types of collisions. So there are collision with impurities or phonons, which do not conserve the momentum at each scattering event. So the electron momentum changes, and a part of the electron momentum goes to either to the other system. Either to the impurities or to the phonons. Or there are particle-particle collision which conserve momentum and energy at each scattering event. And these are the ones that on which we will focus on, because these are the ones that give rise to electron hydrodynamics, and they are basically the interactions that are most similar to what happens in a normal liquid. So for hydrodynamics to hold, so we must have that electron-electron collision occur frequently enough. Frequently enough means that they occur more often than all other scattering types. So be they ballistic or impurity phonons, or even faster than the frequency of external perturbation. So electron-electron collision must be the fastest process in the system, so to be able to establish a quasi-equilibrium. If this would be true, then one would have the electron system would locally be in a state of quasi-equilibrium and would really behave. And one can derive equation of motion that are the type of hydrodynamic equations of motion. And for example, one of the consequences is that if this would be possible, then one could have a flow of the type of Poiseuille flow. So Poiseuille flow is the flow of a fluid in a pipe, by which, since there is friction between the fluid and the pipe, and the only place where there is friction is really the boundary with the fluid, at the boundary with the pipe, between the fluid and the pipe, the velocity profile that one obtains has this shape, which is a parabola, whereas if you think of a ballistic system, which there is basically no interaction between, there is no friction for particles that propagate parallel to the boundary, the velocity profile will be completely flat. So this is clearly very different from the standard ballistic result. If one solves this problem with no split boundary conditions, which means that the particles at the boundary must have a velocity that is 0 in the direction along the boundary, one obtains a resistivity that decreases with temperature, and it decreases with temperature because the viscosity, so because these parameters increase with temperature. And as a result, since there are other mechanisms that will eventually make the resistivity increase, one obtains a minimum in the resistivity. So one expects a non-monotonic behavior of the resistivity. This is what has been actually observed. The first experiments were done in the 1990s by mostly Molenkamp, who studied the transport in high mobility wires, he observed no monotonic temperature dependence. In the case of this nanowire, basically what was done, the electronic temperature was raised by means of Joule heating. So passing a current along the wire, the electrons heat up, and their temperature increases with respect to the lattice, and eventually they enter in a regime in which the resistivity becomes non-monotonic. Now, this at the time looked pretty much like what was predicted by Gurdjieff in the 1960s, which I showed in the previous slide. There has been quite a debate. So actually, it turns out that this is still quite controversial. So there are other possible interpretations for this phenomenon. So it's not entirely clear that this is actually due to hydrodynamics. Let me just turn on, otherwise it will. So there is besides this experiment, there is not much more evidence. There has not been much more evidence for the rest until the 2015, basically 2015 to 16. The reason for this is that we want to require that the electron-electron scattering length is the shortest in scale of the problem. So electron-electron collision occur frequently enough. But actually what happens is that in reality, electron-electron scattering is always slower than all other electron impurity or electron phonon scattering. And the reason is that at low temperature, Pauli blocking leads to a slowdown of electron-electron collision. So this typical length scale of between two successive electron-electron interactions grows dramatically. And at high temperature, actually, most metals phonons dominate. So most of the time, every merging hydrodynamic behavior is already destroyed at birth. And what one finds is that essentially one recovers the standard diffusive transport, in which is due to electron scattering off against impurities or phonons. In all this, of course, being in Manchester, I cannot avoid to mention graphene, which was in fact the turning point for hydrodynamic transport, after which, of course, hydrodynamic transport has been observed in many other systems, included two-dimensional electron gases. So, but the turning point was really graphene, and the reason was that the system can reach extremely high purities, especially when encapsulating in boron nitride. And it's very stiff, so its electron phonon coupling is suppressed. And this means that there is some hope for hydrodynamics, and in fact, hydrodynamic behavior was observed. So there is a range of temperatures in which electron-electron interactions can dominate transport, and can lead to can give the dominant contribution to the transport, and can lead to hydrodynamic behavior. Now, which kind of experiment one should look for? Because so hydrodynamics basically means that we have a viscosity, and viscosity means that we have some friction that depends on the derivatives of the velocity. So the idea is to make the flow in some way not homogeneous, in such a way that the viscosity is activated. If the flow becomes non-homogeneous, the derivative of the viscosity is derivative of the velocity is non-zero, and of course the flow can become the effect of the viscosity can be activated. And the first viscometer that was developed was essentially at this shape. So this is a kind of a slab of piece of graphene. A very thin contact was placed somewhere, and the current was injected at this contact and taken out at another end of the sample. And a potential was measured between two other points of the system. So in this way, one can measure what is called what was called vicinity resistance, if you want, is a sort of non-local resistance. And the result of this measurement is that this resistance can become negative when the flow becomes hydrodynamic. A very simple way to look at it, although it's not entirely correct, it's to think that one can generate whirlpools in the sample, and these whirlpools essentially push the flow in a direction which is counterintuitive, which is against what you would have in a normal case. So in a normal case, in the ohmic regime, you would have flow going in this direction. In the hydrodynamic regime, the flow has reversed, so one picks up a negative contribution to the resistance. In reality, this the effect of the whirlpools is not needed. So whirlpools and not whirlpools, the flow will always be, but the vicinity resistance will always be negative in the hydrodynamic regime, and the reason is actually due to the extreme non-locality of the relation between currents and potentials that one gets in hydrodynamics, or in general in this kind of problems. Just briefly to mention, one shouldn't be bothered by the fact that the resistance becomes negative. There is nothing strange here, no violation of any law of thermodynamics. So there is no violation of Joule heating or anything. This is not the resistance between the same two contacts along the flow, which is bound to be positive. This is an object that is a non-local resistance, so there is no issue with it being negative. What was done was to model this system and to extract the viscosity, and to compare it to theoretical prediction based on basically diagrammatics, which were published here, but it's not too instructive. But I mean, the good result was that there was a reasonable agreement between these two. Of course, you see that the agreement is not optimal, but there is quite a bit of modeling involved, and it's not so surprising that actually this result looks like this. This was observed in other experiments. I will cut it a bit short, but in other experiment on constrictions, and essentially where the flow, essentially where the conductance of the constriction increases in the hydrodynamic regime due to a sort of drag effect of interaction through the constriction. This drag effect depends on the viscosity, and the viscosity can be extracted in a much neater way and compared to theory, and the agreement in this case is much clearer. So it gives confidence that this observation, actually what we are observing is actually hydrodynamic flow. Same story in the magnetic field. I will cut it short. I will skip this, or studying the importance of nearby gates. Again, theory and experiments are pretty much on top of each other without practically any fitting parameter. So this gives us confidence that these systems behave as hydrodynamic. So hydrodynamic really exists in graphene systems, and it has an important effect, at least in certain ranges of temperatures. Now, there has been much more coming out after all these works. There has been a lot of works in bilayer graphene, the hydrodynamic of also the hydrodynamics of the undoped regime, which I will briefly touch later in this talk, in semimetals and so on. So this field really has become has swollen up after these discoveries. But now I want to talk about another consequence of hydrodynamics. So after I have convinced you that hydrodynamics exists in electronic systems, I want to talk about the intrinsic violations of Wiedemann-Franz law due to hydrodynamics. And the Wiedemann-Franz law, just to briefly mention, is a law, kind of law. It's the relation between the thermal and electrical conductivities. The thermal conductivity, you remember, it's the coefficient which I introduced at the beginning. So the two coefficients control the charge and thermal transport in the system, and they are related. They turn out to be related by a simple relation. Basically, they are linearly related, and this coefficient L, which is called the Lorentz Ratio, has in general this form, which is a universal constant of nature, and many materials do behave accordingly to, especially metals, do behave accordingly to this Wiedemann-Franz law. As you can see, the black line here is this Lorentz ratio here, and you see all the dots are all these materials that do in fact behave, or they are very close to the Wiedemann-Franz limit. Now, this law is not really a law. Actually, it's more like an experimental fact that was observed at the beginning of the 1900s, or maybe before. The law originates essentially from the fact that electrons in metals do conduct both electricity and heat. But in reality, there are several approximations behind this law. So first of all, there is kind of to at least derive this law in a closed form, one should assume that electrons are more or less in a Fermi liquid regime, so they are the temperature is much smaller than the Fermi energy, and this is obviously valid for metals where the Fermi energy is huge compared to the temperature. The Fermi surface is approximately spherical, so there are no there is no strange behavior, no Van Allen singularity, no concave Fermi surfaces, no point-like Fermi surfaces, etc. And collision, another important requirement is that collision equally affect charge and heat transport. And this is true for the electron impurity interaction. But in general, it's not true, and especially is not true, as I will show you later, for electron-electron interaction, which are the dominant scattering mechanism in the hydrodynamic regime. And that's why hydrodynamic regime can, it's a regime in which these violations can be large. Of course, there are many other ways to violate this Wiedemann-Franz law. One can go to higher temperature, where either one deviates from the simple linear behavior, or other mechanism contribute. So, for example, phonons, electron-phonon interaction start contributing. One can consider more complex than structure, energy-dependent scattering again. Phonons can give a non-negligible contribution. Of course, the law rests on the fact that electrons give the dominant contribution to both thermal and electric transport, but although the electron will always give the dominant contribution to the electric transport, they not necessarily give the dominant contribution to thermal transport. So in semimetals do still conduct heat, although they don't conduct charge and heat in the semimetal in the insulators. But of course, in insulators, the heat is conducted by phonons. So phonons can compete with electrons, or any other quasi-particle in the system can compete with electrons in transporting heat. But the question here is more like, okay, is there any intrinsic violation? So if we put ourselves in a perfectly unipolar Fermi liquid, very low temperature, a spherical Fermi surface, but we are in a hydrodynamic regime, and we cannot forget about electron-electron interactions. So temperatures are not so small that we can completely disregard electron-electron interactions. Do we get a violation? And the answer is yes. And the reason is that electron-electron interactions treat charge and heat transport in two very different ways. So if we consider a simple parabolic band electron gas, so the simplest kind of system, electron-electron interactions do not impede homogeneous charge current. And this is kind of obvious because the charge current in the homogeneous charge current is essentially the sum of the currents transported by all the particles. But since the velocity of each particle is p over m, the homogeneous charge current turns out to be exactly proportional to the total momentum of the system. The total momentum of the system is conserved at each scattering event. At each scattering event, two electrons exchange some of their momentum, but the total momentum of the system remains unchanged. So a homogeneous current cannot be changed by electron-electron interactions alone. And what can happen is that viscosity that we have seen in the previous part of the talk can relax non-homogeneous currents, but it relaxes to the homogeneous ones. And then after that, electron-electron interaction becomes ineffective, and impurity or phonons are necessary to provide finite current, to stop current from accelerating indefinitely due to the fact that we are still applying an electric field. So in the absence of impurity of phonon, what would happen when you apply an electric field is that electrons would continue to accelerate, barring, of course, block oscillations and other effects. They would just continue to accelerate in this simple free electron system. In general, this is always true. This is true not just for this special case of a yes. Is there a question? Okay. It's not just true for a parabolic band electron gas, but also for in general for any system which has this requirement of having a convex Fermi surface and so on, as unipolar. Is only one type of charge carrier and so on. And the reason is that whenever we apply an electric field, what we do with we change the occupation function of this band, and we change the occupation function in such a way that we accumulate electrons on one side and we deplete the other side.
Yeah. So.
So. Is there a question?
No, please.
Okay. Okay, so we deplete, we put electrons on one side and we deplete the other side. And but this state that we generate, this state has is a finite momentum state. So electrons are accumulated on one side, so it has a finite momentum. So not only carries charge, carries a current, but it also carries momentum, has a finite momentum. And since momentum cannot be relaxed, the current can also not be relaxed. There is a component of the current that is proportional to the total momentum. This will always be true. There is always a component of the current which is proportional to the total momentum of the system. And the total momentum of the system cannot be relaxed by interactions, cannot be damped by interactions. So there is no weight for that component of the current to be damped. So the current as a whole, at least the component, will not be damped. So there is, in general, the interactions cannot affect the charge current. On the contrary, they can impede homogeneous heat currents. There is no problem with that. Homogeneous heat currents are defined from this heat currents are defined from these thermodynamic relations once it's taken to the definition of currents. And in this case, one defines in the previous case, the electronic charge, of course, is always the electron charge. In this case, there is a sort of thermal charge, which is given by the energy minus the chemical potential. And in this case, when a gradient of a temperature is applied, the fact that the charge changes sign above and below the chemical potential implies that electrons are accumulated on both sides of the parabola. And as well, holes are also accumulated on both sides of the parabola. So at low temperatures, this state carries no momentum, as a zero momentum state. It carries a thermal current, it carries zero current, but also carries zero momentum. So since it carries zero momentum, this state is in a way orthogonal to the momentum mode, which is the conserved mode of this theory by definition, because electron-electron interaction conserve the momentum, and therefore this current can be dissipated by electron-electron interactions. So what one expects that the Lorentz ratio, which is the ratio between the thermal conductivity and the charge conductivity, once one accounts for both disordered phonons and electron-electron interactions, one finds that while sigma as contribution is controlled essentially only by disorder of phonons, the thermal conductivity is further reduced by electron-electron interaction. So electron-electron interaction act as another scattering channel, but only for the thermal conductivity. So, and the result of this is that the Lorentz ratio can go below its predicted value by the Biedermann-Franz law, and also that the thermal conductivity scale as 1 over the temperature. This fact that the thermal conductivity scales 1 over the temperature actually can have important effects for enhancing the heat to charge conversion efficiency, but I will just flesh this out and I will continue. Because what I want to talk about now is actually another regime in which something interesting can happen. So, so far I've talked about a regime in which we have only one type of carriers, so only electrons or only holes would work the same. And what we found is that the Lorentz ratio is reduced below its Bayer value. Now, actually, I want to consider a completely opposite regime in which I have two types of carriers. And again, the standard, the initial system that was studied was in this respect was graphene, or at least graphene is a nice example in which this happens, because graphene at the neutrality point is in a regime in which we have an equal number of electrons and an equal number of holes at finite temperature. There is a little bit of electrons populating the upper band, which comes from the fact that the population of the lower band is reduced by the fact that we have a finite temperature. So, of course, this system has two other features: that the Fermi surface is reduced to a point, it's not anymore a nice circle, and the band structure is strictly linear, so there is no parabolic approximation. And in this regime, the role of thermal and charge current are actually swapped. So thermal current becomes proportional to the momentum, or at least contains the momentum, contains a component that is proportional to the momentum, and therefore it's not impeded by electron-electron interactions, whereas the charge current turns out to be orthogonal to the momentum mode, which is the conserved mode, and it can be impeded by electron-electron interactions. And to see this, again, one can look at what happens when one applies an electric field or a thermal gradient. And what happens is that when one applies an electric field, the population of electrons, let's look at that, it changes by accumulating electrons on both sides of the Dirac point. So the total population, the total state that one generates has zero total momentum. Whereas one applies a thermal gradient, particles are added on the same side of the Dirac point, so it carries total momentum. Notice that this state carries charge, the charge current. Both particles propagate in the same direction. This state carries zero charge current, but carries a finite momentum. So the charge current and momentum currents are completely decoupled in this case. In fact, momentum is now coupled to thermal current. So what happens is that essentially in this situation, since the thermal conductivity is now unimpeded by interaction and the charge conductivity is, we expect a violation that goes in the opposite direction with what we have seen before. So if before the Lorentz ratio was going below its value, its bare value, in this situation it should go above. The standard the standard Lorentz ratio, the standard value of the Lorentz ratio. And this is in fact what is observed by experiments. So in experiments, what is seen is that when, as long as the system is far enough away from the compensation points, from the Dirac point, the Lorentz ratio is equal or slightly below sometimes the universal value, which is this thin line. But as soon as it goes to the Dirac point, the Lorentz ratio shoots up, and it is actually a massive violation. So compared to the violation that one observes here, which is tiny, this violation of interaction in this case, the violation in this situation is much larger. It turns out that actually to observe this violation, actually it's essential to have disorder. And the reason is that the Dirac point is extremely, if there would be no disorder, essentially there would be a singularity at the Dirac point. So one would observe the standard correction up until the Dirac point, and then at the Dirac point there would be a sort of a jump in the thermal conductivity. The fact that we see this effect at densities far away from exact compensation is actually due to the fact that there is disorder. So disorder in this case enables hydrodynamics, so enables the observation of this new hydrodynamic regime in which momentum is thermal current is proportional to momentum, and charge current instead of orthogonal to the momentum. So this ambipolar regime of transport. Now, as I said, graphene is a bit special in all this because the bands touch exactly at the Dirac point, so exactly the compensation point. So essentially, there is no real Fermi surface. The Fermi surface collapses to a point. And so one may argue that, okay, maybe what you are observing is actually due to other effects. So linear band structure, the fact that there is no Fermi surface, so the system is effectively a non-degenerate Fermi gas. So the temperature is always much larger than the Fermi energy. What about in other semimetals, in real normal semimetals, where we have two pockets of electrons and holes, but the two pockets are essentially two non-degenerate Fermi, two degenerate Fermi gases, so two degenerate Fermi liquids. If we look at each pocket, the temperature is always much smaller than the Fermi the Fermi energy. Well, what is observed is actually a reduction of the Lorentz ratio below its bare value. That in these units is 1. So the first guess is, of course, okay, fine. You have changed type of carrier, so you go from a non-degenerate system to a degenerate one, and now you have lost again your you have lost again this funny hydrodynamic regime behavior, which is due to which is what one observes in graphene. But actually, this turns out not to be true. So this argument that I gave about the fact that the thermal conductivity remains proportional to the momentum and the charge current actually is orthogonal to the momentum. So in principle, all these arguments that I gave remain valid. So so theoretically, we would have predicted a spike again of the Lorentz ratio, even in this situation. And in fact, we were quite thrown off by this result, and we try to understand it. It's certainly not due to the different statistics, but actually it's due to the fact that how the measurements are done and what is really happening in the system. So so to understand this, one has to just go a little bit back and understand how the measurements are done. So measurements in the system are done in this. The measurement of thermal currents are done in this way. So one connects two reservoirs to a channel, one hot and one cold. The contacts are insulating, so there is no charge current that passes through this system. So the measurement of the thermal current is done at 0 charge current. And in this situation, when the system is ambipolar, what I can do, I can actually, so when the system is unipolar, this type of measurement immediately means that you stop the charge current from propagating, so you immediately disable the momentum mode. So the momentum mode disappears because it's automatically proportional to the charge current. In this situation, actually, it turns out that I can still make use of the momentum mode. So this make a transformation of the occupation function such that, which is not damped by, if you want, in the language of the Boltzmann equation, is not damped by the collision integral. And the reason is that I can transport both electrons and holes in this system. I can generate a current which is neutral, but which carries a total current, a total heat current, but carries no charge current. So it satisfies the boundary conditions of no charge current flowing through the contact automatically without disabling the momentum mode. So in principle, in this situation, I would have a large contribution to the thermal thermal current. But why don't I? Then the question is, why don't I see a divergent thermal conductivity? Well, the solution of this is, of course, that it's not necessary to. It is possible that due to the impedances mismatch at the boundary, what happens is that not only the total charge current, but also the electron and hole currents are separately equal to zero at the contacts. Or at least they're not necessarily equal to zero. Actually, everything that I will say works also in the case in which these two currents are not zero, but they are not equal to the, essentially there is some impedance mismatch, so they don't equal the value that they would have if they could just, if the contacts would be perfectly transparent to electron and hole currents. So for the sake of the argument, I will just assume that they are actually zero, but in principle, this can be extended to a more general situation. So it's quite a strong requirement, it is not needed. If I do this, if I impose that both electron and hole currents are zero, now the momentum mode again becomes inactive and I recover a unipolar result. So this is a good news because this allows us to understand what happens in the case of standard semimetals. But now the problem, how do we explain what happens in graphene? How do we interpolate from one regime in which, so we have two systems which should behave in the same way, graphene and normal semimetal, standard semimetals, but they do behave in very different ways. And the reason is that actually in all this, what has been left out in all this description is actually recombination. So what happens is that we don't have to impose that the electron and hole currents are zero everywhere in the channel, but what we have to impose is that they are zero at the boundary, separately zero at the boundary. This, however, means that if recombination is fast enough, if recombination is very fast, the currents can be non-zero in the channel and can become rapidly zero at the edges. But if the recombination becomes slow, what happens is that the regions in which these two currents, so what happens is that we get an imbalance between the two currents, and they basically these regions at the boundary start behaving as unipolar regions, and behaving as unipolar regions, they basically the total resistivity will be the sum of the resistivity of these three regions. But when the recombination time becomes very large, these unipolar regions at the boundary become very large, so they completely squeeze out the ambipolar regions in the middle. And therefore, what happens is that one recovers one can go from a perfectly ambipolar regime when the recombination times are very short to a perfectly unipolar regime when the recombination times are very long. And these are the two regimes of graphene, which behaves as a perfectly ambipolar system, and conventional semimetals, which essentially behave as perfect unipolar because transport is unipolar all along the channel. And the reason why we believe that this is actually what happens in graphene or what happens in semimetals is that the crucial difference between graphene and the other semimetals that were studied is that in graphene, the two pockets of electrons and holes occupy the same point of the Brillouin zone, so they can quickly thermalize and reach the same chemical potential and the same temperature. They can quickly recombine, so you can have all these Auger recombination processes and so on that thermalize the electrons with the holes locally. Whereas what happens in standard semimetal is that the two pockets are far away in the Brillouin zone, so momentum conservation and so on lead to a slowdown of these equilibration times between the pockets. So this is the what we believe is going on in this system. Of course, one should have a key observation for this will be to observe how the resistivity scales with the length of a channel, and going from unipolar transport in short channels to ambipolar transport in long channel. Now, short and long channel, actually here, since recombination times can be pretty long, actually, typical systems which are already pretty macroscopic, they are still in the short channel limit. So it's actually quite challenging to keep sample purity at such large distances. With this, I conclude, and I just hope I convinced you that this new regime of transport, well, it's extremely interesting. So there is by now enough proof that this regime of transport exists in the charge channel. So there is plenty of proof that viscous charge flow sets in graphene or even other systems. But we have there are interesting predictions. Probably there are more predictions that can be laid out about thermal or thermoelectric transport, which have yet to be confirmed and have yet to be completely proven. So with this, I conclude, and thank you very much, and I'm ready to get questions.
Okay, thank you for the nice talk. I think we're good on time. Any questions from the audience? Okay, let me ask you the first question. So this is pretty general effect. You get the reduced Lorentz ratio if you have a semimetal with a how to say negative indirect gap.
Yes. Okay. Negative indirect gap.
Yeah. So it's yeah. So for those materials, you will expect to have a reduced Lorentz ratio. And
yeah.
Okay, but is there any length scale associated with that? Because you said that you need the electron-hole pocket to separate it in momentum space.
So they are separate in momentum space. So the length scale is set by the typical equilibration time between the two pockets. This can be pretty long. I believe they can reach even microsecond in some cases. So this is the typical time. So that it takes. So this length scale is given by the by a square root of a diffusion constant times this time. So the diffusion constant is controlled by the density of states of the system and so on. But the real crucial thing is actually this recombination time. Now in our theory, we didn't try to quantify all the details. So that is, but I mean, order of magnitude. From the order of magnitude, we find that typical experiments are still in the kind of a short channel limit in which essentially all the transport becomes unipolar. One should go to very large systems to really see this effect of the ambipolar region of the channel.
Thanks. Any other questions from the audience?
Yeah, can I ask a question?
Yeah, sure.
So there has been a lot of progresses and activity on this subject in the last several years. I'm just wondering, what are the the important questions to answer, left to answer on for this topic, hydrodynamics?
You mean which questions are still open?
Yes, yeah.
Well, yeah, well, the progress has been very large. So there are certainly questions still open on, well, I can tell you what I see as interesting topics in this field. So, for example, the role of the interplay between interactions and band geometry. I think it's a topic that has been quite explored in the context of Weil semi-metals, where one has many effects, but much less in systems like two-dimensional semi-metals. So this is one of the topics. At this point, I would say there are many open questions. Well, okay. I think there are mostly open questions related to thermal and thermoelectric transport in hydrodynamics. So from the experimental point of view, to my knowledge, this enhancement of the Wiedemann-Franz ratio, for example, has been observed in graphene, bilayer graphene, and nothing else essentially. So there is a kind of lack of this observation in other semi-metal, possibly because, as we said, in typical systems, the pockets are far away in energy, so it's difficult to observe a transition between it's difficult to observe this new regime of hydrodynamics. So so there are mostly questions related to how to observe experimentally these effects, and very little.
Sorry, I'm on another call at the moment.
And very little has been done on thermoelectric transport. What I can say.
Okay, thank you. I think Phil has a question.
Yes, on the question of improving thermoelectric figures of merit, I was just wondering in what context the thermoelectric effects are of significance, or is this just purely academic, or is there some idea of an application that could be useful for thermoelectricity? It seems it's going in the sort of the wrong direction rather than the direction you need.
No, okay. So this secondary hydrodynamics, yes, goes in the wrong direction. The first one actually goes in the right direction. I can show you briefly why. So this first type of hydrodynamics in which the Lorentz ratio is reduced, actually, most of all, it's in which the thermal conductivity goes as inverse to the temperature. What happens is that the more you heat a certain point of the system, the less it conducts heat. And what happens is that, for example, if in typical, so one way in which one can produce a thermal current, a charge current, or a voltage in graphene is to use a p-n junction. So using a p-n junction, one can tune the Seebeck coefficients to have opposite signs on the two sides of the junction, and by heating the junction, one can produce a voltage. So this actually is done in experiments. So shining light on a p-n junction and producing a photovoltage. Now the question is, if you reach this hydrodynamic regime, now what happens is that the thermal conductivity becomes a decreasing function of the temperature. So what happens is that heat tends to accumulate in regions which are already hot. And since the region that is hot is the region that is active for the production of the voltage, actually this enhances, dramatically enhances the figures of merit. Now, this is of course is a theoretical proposal. It's still yet to be observed experimentally. But I mean, we believe that it's possible. Now, the problem is that observing this in graphene may be a little more difficult because essentially phonons will eventually dominate the thermal transport. So one should find the material in which this effect is not shunted completely by the phonons. So in which electrons actually give the dominant contribution to the current, to the heat transport. Does it answer your question?
Thank you. Yes.
Yeah. Okay.
One more questions, Harsh. Please go ahead.
Okay, well, actually, I have like some very naive questions. I don't know if this is like, if there's only one question, I hate to be the one to ask this. But one thing I was wondering is that you gave us a very nice historical overview of the subject. I was wondering if there must be some work in helium-3, the normal state of helium-3, because that has got to be hydrodynamic, right? There is no other.
Possibly, I'm not aware of it. So yeah, I believe there are. Well, okay, this effect has been observed in many systems. So even in I didn't mention, but even in 2DEX, in semiconductor quantum wells have been, most of these effects have been observed. Most of the hydrodynamic viscous flow have been observed. I believe it should be observed also in L3, and probably has been observed. I have not.
Well, simply because there's the collisions are the dominant mechanism over there.
No. In fact, yeah.
Very much.
I mean, there is nothing else. So yeah, it should be. Yeah.
I was also curious about. So sorry, you said one question, but I'm going to ask two, which both have very short answers, I think, because they're both rather naive questions. One is about, I asked the previous speaker this as well, but I'd like your opinion. I mean, what are the prospects of maybe getting into a turbulent regime with electrons?
Okay, so turbulent regime, one has to have, in a way, small viscosity, because turbulent regime emerges at small Reynolds number. Now, the problem of this system is that the viscosity is huge. So graphene has a viscosity, well, when you calculate the viscosity, you get viscosity that are 1,000 times the viscosity of honey. So it's very difficult to reach a turbulent regime. Maybe, I don't know if in the semi-metallic regime, somehow the turbulence can emerge. However, you have the problem that you already have a resistivity due to the interactions themselves. So it's already, all the viscosity effects are masked by the fact that you already have essentially a resistivity to begin with, just due to interactions. So I'm not sure that it can easily be found because Coulomb interactions are very strong. So.
Okay, well, thank you.
Yeah.
Okay. I think we're a little over time, so let's thank our speaker again. And if you are interested, you can stay a little bit longer. So we have informal discussion.
Thank you. Thank you very much for the invitation.
Let me stop recording.